Okay, we have still a few students arriving, so we'll hold off here just a minute or two. Hello, everyone. Thank you for joining us. We'll get underway here in just a moment. It's a bright, sunshiny, nice spring day here at Purdue. I hope you are enjoying good weather as well. Most of the students know me. I'm Dave from Saturday Morning Astro at Purdue. It's nice to see your faces, and even if I don't see your face, it's nice to have you here. All right, it's 11:02. We may still have a few people entering, and we'll admit them. Alan, I'm going to make you co-host, and would you admit
Sure.
students as they arrive? Okay, so thank you all for being here. Welcome to the March Saturday Morning Astrophysics at Purdue. This is kind of a special event because we have a special guest, and we're going to ham it up a little bit. I hope you don't mind. I hope you bear with us and enjoy the humor. Before we get started, we've got a couple of TAs, teaching assistants, joining us, and I'd like to have them just say hello and say who they are and what they do and introduce themselves. Excuse me. Mariana, can we start with you?
Hi, my name is Mariana. I'm a sophomore here at Purdue in planetary science.
All right, thank you. Alan, how about you next?
Hi, I'm Alan. I'm a junior in physics, and I think I've met a lot of you already.
And Vic.
Hi, I'm Vic. I am a senior in physics here at Purdue.
That means you'll be going on to something else in a few months.
Yes, I'll be going to graduate school.
Are you, do you know where? Do you have any definite plan, or are you still deciding?
I have already decided. I'll be going to Northwestern for graduate school in astronomy.
Terrific. Well, I hope we can still count on you to help us out in SMAP once in a while.
For sure.
I wanted to, first of all, say to our students, you may come up with some questions while we proceed this morning. So if you want to have a paper and something to write with handy, that might be beneficial, that you can, excuse me, remember your questions and we'll address them at some point. Also, if during the presentation you have a question, you can go down to the reactions and raise your hand or just unmute yourself. But if either way, it's okay to ask questions as we go along. I also wanted to mention two other things, and that is, if you haven't done so already, subscribe to, excuse me, subscribe to our YouTube channel. We have some cool things there. You'll be in the know of what's coming up. I would mention, we just put up a video, maybe you've seen it, about constellation tubes. One of my students created a real cool video using an apparatus like this with holes punched in the end to view constellations. It's a cool video, and it's a good way if you want to learn constellations. It's a good way to practice learning constellations. You could even identify the major stars in those constellations. So I think that's all I have to say in the beginning. I'm going to proceed with introducing our guest. Who can tell me who our guest is? Somebody raise their hand and tell me who the guest of honor is. Or just unmute yourself and say it. Daniel?
Kepler.
Yeah. What do you know about Kepler, Daniel?
He learned a lot of stuff at about our solar system.
That he did. That he did. Okay, let's leave it at that, and let's turn it over to Professor Kepler. Are you there?
Here. Okay, so yes, sorry to disappoint. Kepler couldn't make it, but the impersonator of Kepler, myself, Professor Dan Milisalovic at Purdue University, is going to sit in. You gave it away. There's no hammy humor here. It's all real humor, Dave. Welcome, everybody. It's great to be a part of this. I think we're going to make the most out of this virtual format. Shall we just take it away, Dave?
Just take it away.
Just take it away. All right. So the whole point of this is to see what your experience was, and we're going to discuss what was and what wasn't learned. And I really want to hear about, if you attempted the unit, any of the challenges that you faced, because I mean, I can show my notes, like a lot of like little lists of numbers and scratching out boxes, and wasn't straightforward. So of the people that are here today, can you tell me a little bit about if you did it? And don't worry, it's okay to say if you didn't do it. Can I go through people actually? So Drew, I see you. Did you try it?
I started it. I didn't get all the way through it, but for the most part, for what I got through, it was fun. Okay, well, fun is not the word I would have used, but that's good. How far did you get? I finished like the first table, and then I did the measurements of like the around the circle with like the string, but I didn't get through counting all the squares. Ah, okay, right. So this table where you had to make measurements from the sun to asteroid, right? And then converting. And then the other one was the string one, right? Okay. Yeah. Yes. Yeah, and then the counting, right? And then you got frustrated. Okay. How about Lily?
I didn't complete it because of school, but I did read through it all and also watch the video, but it looked like a lot of calculations and stuff.
Good. Okay. Did you do any of the measurements?
No, but I did kind of see where it was going with like counting the boxes and seeing like the second law of where it sweeps out equal areas and equal times.
Oh, hold on. We're going to get there in a second. Yeah, great. Daniel.
I finished the entire thing.
Of course. Wonderful. And we'll come back to your results in a moment. But since you completed the whole thing, can you tell us about your experience?
It took a while. That's what I could say.
And how about counting the boxes? Because we know that's challenging.
They were almost entirely the same area, but like they were off by a little bit.
Uh-huh. Okay, good. Trends. We'll get to that in a moment. Great. Luca.
I didn't really have time to do it because of school and stuff.
Totally legitimate issue that we all confront. Tell me something. Did you have a chance to read through it at all? Or watch the video?
I may have read through it like a couple weeks ago, but that's it.
Okay,
and the video, I didn't watch the video.
You didn't watch. Okay, no, that just helps me set context of if I'm going to review some things to make everybody on the same page. No problem. Very good. Hey, what was the homework that kept you occupied?
I had a lot of projects, and there was also a bunch of tests and quizzes that I had to study for.
Tests and quizzes. It never ends. Okay, Kate.
No, I just registered like this afternoon, so I didn't do it.
Okay, no problem, Kate. And had you watched the video?
No.
No. Okay. Homework? Sorry, Kate, was it homework that kept you busy?
Yeah.
Yeah. Did you ever hear the Jerry Seinfeld joke? Why do they call it homework? You're not working on your home. Anyway, Nicholas.
I watched the video and read through the paper. However, I had my calculus and chemistry finals to work on this week, so like.
Yikes. Understood. Okay. And I'm sorry if I get the name wrong. Niat.
Yeah, I watched the video, but I didn't have time to like do the calculations and stuff because I had a science project.
Science project. And then, and did I get the name right? Can you pronounce it for me?
Well, yeah, this is my sister's like iPad.
Okay, so it's not your actual name?
Yeah, my name's Jakob.
Jakob. Okay, that's helpful to know. And I see Fedora.
Yeah, that would be me.
I'm sorry, Fedora, you're a little soft. You did or didn't do it?
No, I have no idea what project this is because I don't remember finding something in my email.
Oh, okay. But you came for the fun anyway. All right, great. So the task at hand was, there's this sketch, and I could share it on a screen, but let's just do it like this. So here is the sun, and this is tracing the orbit of an asteroid around it. Okay. And this assignment in general is supposed to help you understand or get familiar with Kepler's 3 laws of planetary motion. Okay. The first one is illustrated just with this plot. Do you notice how the orbital motion is not a circle, it's an ellipse? Okay.
Yes.
And that is a general law or empirical regularity that we observe in the universe. Okay. And that actually caused a lot of troubles for centuries. People wanted the Earth to be in the center of the universe and all the other planets and the sun and the moon orbiting around the Earth in perfect circles, because that makes most sense. Our hunch is Earth is most important, so let's put it at the center. And circles are very, they're symmetrical and the universe should be perfect, but it's not like that, okay? And it took Kepler decades of working with, the measurements. He didn't have the luxury of looking at the solar system from above like this and seeing the path, right? What do we have? Our measurements are looking at the planets at night and seeing how they move with respect to stars. So using that data and then fitting it with orbital motions. And he found that you couldn't do it with circles, you needed to do it with ellipses. Okay? And the assignment just flat out tells you, and or the video shows that the first law of planetary motion is that all planets orbit the sun as an ellipse with the sun at the center of an ellipse, which is actually a focus, okay? A pure circle has one center, but an ellipse, because it's kind of like stretching it out, it has 2 foci. And here's one focus, and then another focus would be symmetrically opposite on the other side, okay? So it straddles in one of these 2 focus points, right? The activity took you through the other portions of that. And it asked you to do a number of things. Let's see, Daniel, what was the first thing we had to do for this? Are you looking at
measure the distances from the sun to the different spots where the asteroid would be every year?
Right. So here's the sun, and then looking as it traces around, there's these markers, and each of these is 1 year in separation. So we'd measure the distance at these positions along the orbit to the sun. Daniel, I heard that you told us that you did it. Do you have a way to share that? Would you be able to do that?
I have it on a Google Sheet. I just need to share my screen.
Yeah. Can we do
Daniel?
that, Dave, or should he share the link with us? What's easiest?
Daniel, I can make you co-host and you can share your screen with us. Is that okay?
Do we trust Daniel enough to give him co-host privileges?
I think we're safe. Okay, Daniel.
Okay, Daniel.
You should have the ability now to share your screen if you can. Have you done that before?
Sounds like he's working on it. Well, anyway, as Daniel's, oh, there we go. Oh, it made it an Excel spreadsheet. I like it. Uh-oh, there's my face. Get it away. Good. He even plotted it. Love it. Bravo. So those are the 3 plots. Let's go to the first one. So we have, yes, we have year number and plotted on the x-axis, and then distance from the sun. And that kind of makes sense, right? It'll be at year, this one it's closest, and then because it's an ellipse, there's going to be a far portion at around year 6, midway. The whole orbit takes 12 years, right? So we see this curve that goes up like this. Fantastic. Okay. The other part was to plot, let's see here. Table 1, and then table 2 was, a combination of area swept and then the average speed. So let's see here. This is chart 2. Go to chart 2. So that was the one where most people gave up, and that's fine. We have busy lives, but it encompasses, the task of being able to count up using this grid square all the squares that are occupied. Okay. So I love the way he's plotted it. Do you see how, starting from 0 and then up to 300, there's no, depending on the error uncertainty, and we'll talk about that in just a second. Do you see how it's relatively flat? Okay. So the distance was changing, right? But the area swept was the same, and somebody gave that away earlier, but this is what this graph is hinting at, right? Daniel, you're doing a wonderful job following along. I need you as an assistant, right? Oh, and by the way, that was one of the other parts of the YouTube video, and we can talk about that afterwards, was Kepler was assistant of Tycho Brahe, and that's where Kepler got the observations to be able to make these calculations. And then chart 3. So what are we plotting here? The x-axis has that year number again, and y-axis is average speed. So we notice that year 0, where it's closest, we have the highest velocity. And then as it goes further away at around year 6, okay, what's happened in the velocity? It's going to its lowest point. Daniel, these are fantastic. Well done. Okay. So tell me about your strategy for measuring the boxes, Daniel.
I just counted the squares.
1, 2, 3, 4, 5, just like that?
Yes.
Up to 300 plus? Wow. So my strategy was, I wrote down, I go down one row or column, and then I'd write a number, and then I kept writing down the numbers because I kept losing count at like 97, 98. Where was I? And then I go back and start again. So I went column by column. That's the way I did it. I also tried to do, boxes at a time and fill that in. Anyway, you notice there is challenges because not all the boxes were completely filled, right? You'd have regions where the ellipse would cut through a box incompletely. Okay? So these days, we have a computer, and it's much easier to measure area defined in a region. Okay, but Kepler didn't have that, and he would have to resort to other means. You could use trapezoidal methods, or in our case, just measuring it. But measurements are always associated with some kind of uncertainty, right? So let's see, who did the measuring with the string? I think Lily, Drew, either of you try with the string? Drew, you tried, is that right? Yes. And did you have a string handy on you?
I had some yarn.
Yarn.
I just made
okay.
sure not to like stretch it.
So here's another thing you got to learn. If you're going to be in science, you got to improvise. Okay. So maybe you didn't have a scientific string that was, because, so for instance, I was looking in my drawer, what am I going to use? And I thought, oh, rubber band. I can just rip it in half and measure it around. But what's the problem with a rubber band? It's not solid, it's got gives, right? So it wouldn't be necessarily an accurate measurement. So I dug around a little bit further, and I got my earbuds rather, and it was fine. I just had to be careful on where I pinched it, okay? But the problem is there becomes a limit on the accuracy for which I can, or let's say the precision with which I can measure distance along that, right? So it would be, putting around and then like this, and then using the handy dandy ruler that Dave got me here and measuring it up against, right? But I tried to reproduce a measurement a couple times, and I found that there was an uncertainty of about 0.2 centimeters. So what you can do is you can show that represented in your graph. So Daniel, next time you're asked to do a task like this, you can think about the uncertainty associated with it. So I'm going to share my screen right now. And here's graph 1. So this is measuring the sun to asteroid distance. And you see here, maybe if I do this, make it larger. And of course, these graphs are in the way. Let me move that and move this over to the side. Do you see these? These are called error bars. Okay. So this is representing that my measurement was what, 5.02, but it could have been a little bit higher or a little bit lower. Okay. So when I connect these points, it's just these error bars are showing that, I favored this measurement because of my uncertainty, it could have been a little bit higher or a little bit lower. Okay. So that's how I represent scientific data, to show that, yes, I made a measurement, but it's associated with some kind of uncertainty. That uncertainty is especially important if you're looking for trends. So do you see how this measurement is very different from that measurement, even accounting for the uncertainty? Does that make sense? Whereas this measurement compared to that, when you take into consideration the uncertainty, I could fit a straight line through some of these points here. Does that make sense? I don't want to be just talking to myself, but interrupt if it's not clear.
Professor Kepler, I have a question.
Sure.
First of all, can you enlarge that graph to full screen, your Excel sheet?
Does anybody know a quick way to do it for the graph? I mean, I can do this, and I can do this. How about that? There we go. We're getting there.
Sure. And then can you tell us where those the amount of error comes from? Is that generated by the Excel program?
No, in this case, I quantified what my uncertainty was, which is, and there are different ways to do that. There we go. In this case, I tried to measure the same segment multiple times. I think I did it 3 times, okay? And I found, let's say I measured 5.1. And then when I did it again, I got 5.15. And then when I did it again, I got 5.05 or something like that. So that gave me a sense of the uncertainty, right, between the maximum value and the minimum value. So then in an Excel, you can add error points to measurements. And that's what I did. That answer your question?
Yes, thank you.
Great. Okay, so that was for this. We see a clear trend. Okay, so this is the distance. We can see that clearly that it's getting maximal right around halfway through the orbit. Now let's look at what was probably the most painful part of the assignment, is measuring the area swept. Okay. Now it's funny, looking at the measurements from Daniel versus mine, I think he had less uncertainty and scatter in his points compared to me. So Daniel, kudos to you for that as well. So here again are my points. And then what I did is I reproduced for a certain region, the same region. I tried to count it again and I got a different number. And I tried to get a sense of the uncertainty in my counting. And I did it rushed. You know, I could have done it more precisely if I brought it into a program that can define regions and measure it. But just by eye, this was kind of the uncertainty. Now, this is what I was talking about, looking for trends. Do you see how I can basically draw a straight line through all these points within the tolerances of the uncertainties? Do you agree with that? Okay. So now scientifically, I would say this is consistent with a straight line. I couldn't say that with this because clearly these points are different from those, even within the uncertainties. But here, okay, this looks like a constant flat function. Okay. Again, point by point, you wouldn't necessarily say that, but when you take into consideration the uncertainties associated with the measurement, all of a sudden, I could see a flat point out of that trend. Okay. Why am I belaboring the point? It's that so much of science relies on measurement. Those measurements can have inherent uncertainties, and you may think you see trends in data that aren't actually there, right? And historically in science, it's happened many times where they've been misled by few data points measured poorly to make big sweeping claims. Okay, the last graph. And again, I have these uncertainties associated with it. And this is plotting, again, this is average speed. So taking that distance traveled divided by the time in a year for each of the segments. And we see that the speed, right, as a function of time around the orbit, it starts off at maximum speed closest to the, as we go in graph one. Yeah, graph one, this is distance. So at the smallest distance, actually that's good to show them side by side, isn't it? Let's do that in real time. So when the speed, the speed is greatest when we are closest to the sun, and then we are furthest away, that's the slowest speed. So can somebody put into words how these two graphs make sense with what we see here with the area swept? I hope I'm phrasing that. I want you to explain the fact that the area seems to be constant through each of these yearly segments. Explain that with regard to these two graphs that show the distance away and the average speed. I'll wait here all day. Somebody give me a guess. Drew, you're kind of putting your hand up. Sure. You're muted. Oh,
there it goes. So like, the further away it gets from the sun, the slower it's going. So like, the distance from where it was at 1 year to the next year gets smaller, which kind of cancels out the farther distance from the sun, something like that.
That's right. Do it with your hands. Just what you just said. So here's think of it like this. So here's the sun, right? And you've got an orbiting body, right? So what's going to happen closest to it?
It's going to go faster.
Trace it out. Right. Well, hold on. You're kind of going the same speed the whole time. Exaggerate it a bit more. Okay, great, right? So it's going to zip it around and then going to go slow, right? And then it's going to get faster and zip around, okay, right? So that fast speed, you're going to sweep a greater distance, right? But you're closer in. So that's how Kepler's second law works, okay? So planets sweep out equal areas in equal times. Okay. Does that make sense? So that's Kepler's second law. Okay, since it was Daniel that pushed onward, Daniel, do you answer the questions?
I forgot to answer those questions.
Okay, so we can go through them quickly as a group. I don't know if you have it up in front of you. So one of the questions identifying the perihelion and the aphelion. So the perihelion is when the asteroid is closest to the sun. Let's show that graph one more time. Like this and like this. Okay. So the average. This question is specific for graph 3. Okay. So the perihelion is when and by the way, the peri is closest, helion is sun. So that's where that word is coming from. So closest to the sun in this graph is going to be here. Okay. And then furthest away, the aphelion is going to be here. Great. All right, and then there are distances, average sun, that's fine. We did all that. Okay, the last one now, Kepler's third law. And the activity asks you to do this guess and check, which maybe somebody did, but most likely not. At the end of the day, oh gosh, this is where I wish I had a whiteboard that wasn't so far away. But does anybody know offhand? I mean, we'll just cut to the chase. Kepler's third law of planetary motion. No? So Kepler's third law of planetary motion can be stated like this. P squared equals d cubed. The period of orbit is equal to the distance cubed. Now, you have to use the right units to make that work. Otherwise, there's a proportionality statement. I don't want to get into the math too much, but hold on. Should have come better prepared here. Let's see. I got right here. So we see that. Is that the right way for you? Because for me, it's backwards, but for you, it's the correct way. Nod yes. Okay. So period squared. So that's the time it takes the orbiting body to go around the sun. What's the period of the Earth?
1 year.
Yeah, that's right. Brilliant, Lily. Okay. D, to make this work and with just simple equal signs, has to be in astronomical units. AU, and this has to be year. Okay. Can anybody tell me what an astronomical unit is?
Average distance from the Earth to the sun.
Great. Okay, so what's the distance of the Earth in AU? Hold on, Drew, you've been answering a lot. I'm gonna pick on Kate.
I don't know.
Think about it, Kate. We just heard that the definition of an AU is the average distance from the Earth to the Sun. So what's the distance of the Earth in terms of AU? Nicholas, you want to give her some help?
It's 1, isn't it?
1. Yes. Yes. Simple, right? It's the definition of an AU is distance from Earth to the Sun. So 1 AU. That's the definition. Okay. The other planets will have does that make sense? Yeah. Maybe I phrased it confusingly, but that it wasn't meant to be tricky. Okay. So does it work? P squared 1 year. Okay. 1 squared is 1. And then 1 cubed is also 1. Okay, great. That works. Let's try some others. In this chart, I don't know if you have it handy, but let's do Mercury first. So the period is in days. So I need 88 divided by how many days in a year? 365, right? Okay. And then in this chart, it also tells me the average distance in AU, and that's going to be 0.39. 0.39. See what I've written here? P squared equals A cubed, but hold on. Question mark. Let's see. Does anybody have a calculator? Let's see. I'm going to do it in front of everybody. I don't know if you got a calculator at home, but let's see. 88 divided by 365 is about 0.24, and I'm going to square that. What do we get? Anybody doing this at home? I get about 0.058. And then I'm going to do the other one, 0.39 cubed. Whoa, I got 0.059. Good enough for government work, as they say. All right, let's try another one. Venus, okay? Venus. So, and I'll say it aloud. The period of Venus is 224.7 days. And the average distance is 0.72 AU. So if I do 224.7 divided by 365, and I do a squared, anybody doing this with me? I get 0.379, and then I'm going to do 0.72 cubed, 0.373. Whoa, we got a trend here. Okay, so they're getting the, that we'll forget that last decimal place. That's fine. That's don't worry about it. Anyway, if you were to continue, you would see that the trend holds. Okay? So if you measure the period in terms of years and the distance in terms of AU, which is relative to the Earth, right? You'll find that P squared equals A cubed, right? D cubed. So the great thing is we started with the planets. If you were to continue with the other planets, you'd find the same trend. It also works for anything orbiting the sun, right? Including the asteroid trajectory here. All right. So we've now gone over all 3 laws of Kepler's motion. I'm going to open it up to questions. Or Dave, if you think there's anything else that could be helpful to review right now.
So should I refer to you still as Professor Kepler?
No,
Or
no, we're over that.
okay, all right. So I had a couple of questions that came in by email. One you kind of touched on when you talked about perihelion and aphelion. And somebody asked, I can never remember the difference between perihelion and aphelion. Where do the words come from, and what's a good way to remember that?
That's great. I forget it myself, actually. That's I know helion is sun, and then for instance, there's perigee and apogee. The G, that's with respect to the Earth, right? So that part of it, but the ap and the peri, I mean, who's taken Latin? I'm pretty sure those are Latin origins. And yeah, everybody has their own mnemonics. You'll have to make one of your own. I remember a video game maker called Apogee. And Apogee, and I always think, okay, they're like really out there in their thinking, really out there, and then how they create games. So that always made me think, oh, it's the furthest point. So aphelion would be furthest from the sun.
Okay, good. If anybody has a question, raise your hand or just mute yourself and ask your question. It could be about today's topic or something about Kepler or his time, or what have you got?
I see Lily.
Yeah, so those calculations weren't exact. Is that due to like that it's a proportionality? Like how did that affect the reason that we didn't get the exact same number?
So that's a great question. It may come down to the precision that offered in the measurements here, okay? And there are other influences that go beyond that. Oh gosh, you caught me on the details. I always thought that it was good enough, but there are certainly other influences that go into that relationship. It should balance out. And I mean, also realize that some are going to be more influenced by other planets, right? So it's not just the sun. And actually, going further, these are empirical laws, right? So it can make you predictions, but there's no, why is that, right? So it was Isaac Newton later who who derived these same laws in terms of gravitation. So it's gravity that's, that works out to these things. So there's also the gravitational attraction of other bodies that will influence to some regard. Great question. And if you're thinking of other things to ask, I do have a slide or two I can share about Tycho and Kepler and research that I do. But I leave it open if there's anything else on this topic specifically. Did we convey enough of the three laws of planetary motion, right? I've done this lesson many times, and students routinely coming away thinking that the orbit of Earth is highly elliptical like this. And you know what? That's wrong. Okay? It's a very subtle deviation from a circle, but it's significant enough that it ruins your ability to carefully predict motions of planets. Okay? So that's why it took Kepler so long, because everybody wanted a circle because it seemed to be working, but it wasn't good enough. And in fact, going back to this idea of measurements, Kepler wanted to work with Tycho because Tycho had the instruments that were making the best measurements possible. So instead of error bars like this, right, where you could fit a huge smattering of curves, imagine when your error bars start getting really small. So it forces you, it narrows the parameter space that your model can fit. And actually moving forward in your careers, that's actually something to be aware of. If you know of a new instrument of higher precision than before, right? That's something you want to take advantage of, because you'll be able to narrow down possible models much better than people before you. So that was a strong motivation for Kepler to work with Tycho, because he had all these observations made by the best instruments around.
Professor, Fedora had a question. So could you go ahead and ask your question, Fedora?
That's in the chat. Okay, go ahead, Fedora, yes.
Oh yeah, I also sent it to you. It's just that, would this law be similar in other solar systems?
Universal, yes. And it applies to stars orbiting as well, yes.
Thank you.
I have a question, if that's okay.
Yes.
So, since Earth and all the other planets travel in ellipses, or not you know what I mean.
That's right. Good language, yes.
So, why do we not all get literally annihilated by the sun every 6 months, since we get closer?
So much to unpack in that question. So one thing, remember what I said earlier, it's an ellipse, but it's a subtle ellipse. Okay, so there won't be a huge change in distance, right? That's one. Two, would you believe that we're actually closer to the sun in the winter than we are in the summer? Okay. And the changing of the seasons have to do with the Earth's tilt, not with the distance to the sun. I could unpack more, and that's a whole other lesson, understanding Earth's orbit around the sun and changing of the seasons being due to tilt. Have you done a lesson like that, Dave?
I don't think we've put one together yet, but you could get started on that soon.
Yeah, and I got great people to help me. Okay.
Yes, we do.
But Nicholas, just walk away understanding that the distance change is very subtle, important, but subtle, okay? And in fact, it's not the distance that causes the changing of the seasons, it's just the fact that the Earth has a tilt and the position of that tilt with respect to the sun as it orbits around throughout the year. Does that answer your question?
Yeah, that answers my question. Thank you.
Yeah, I'll just follow up on your reference to future lessons. Some of you may have some good ideas about topics that you would like us to present. If you do, please email me, and those are things that we can consider. We are always looking for new ideas, so we'll look to you. What other questions do you have? Dan, I have a question. While other people are thinking, I have a question that came in by email, and that was: is there a relationship between the radius of an orbit and how elliptical it might be? So, does a larger radius mean that it'll be more or less elliptical, or is there no relationship?
Sorry, to understand, the radius of the orbit?
Yes, the radius of the orbit. Okay. So for example, if you take Neptune's orbit versus Venus's orbit, the fact that Neptune is a lot further away, is it likely to be more elliptical or not necessarily?
So I wish I had a display to be able to show you that. Mercury's orbit is actually much more elliptical than the others. And I have let me follow up on that. It's not that easy. It really boils down to the dynamics of the initial orbit and how it was set up, right? I will, let me follow up on that with a table that I have that shows the ellipticities as a function of the planet, and it's not a neat trend, let's say. Yeah. In the time that's remaining, I know I want to open it up, keep the questions with regard to the activity, but I do want to share something that ties into, ties both this activity with, let's see here, just a moment, sorry, with my own research. Here we go. This is what I want. And okay, actually, no, a couple things. So on to your point, I did find this chart, so I'm going to share my screen. So you see what I'm seeing here? So this is eccentricity, which is a measure of how elliptical it is. And you can see that Mercury is much more elliptical than Venus, right? And then we have the Earth, which is more, and Mars. But then Jupiter, further out, has less ellipticity. Do you see that? So it's not straightforward. Okay, how about I show this real quick? Or not? Okay. I just want to do a plug for my own research. And I hope you have an opportunity to visit Purdue when I'm going to be giving one of these talks about the research and the exciting things we're doing in the time domain astrophysics group. And maybe you'll think about coming to be a grad student here, or at least an undergrad, and do work. We have some people that have worked in the group. Vic has been with us a long time, and Alan's also participated. So the point I want to make, so these were astronomers keeping very close watch on the sky, and during their lifetimes, they noticed new sources. They were called guest stars for a while because they showed up unexpected. Right? And what they ended up being is they weren't living stars, they were stars that exploded, supernova explosions in our own galaxy. Right? When that happens, because the energy output of a star exploding is so large, is that it can become so luminous that it's visible potentially during the daytime, and it can last for many months or a year or beyond. This is an image of an etching showing dramatically Tycho staring at the guest star, which happened in the year 1572. Now, the cool thing is we can go back to that site today. Let's see here. And see what it looks like. And we actually see the remains of the star. Oh, hold on. We'll get to Tycho in a moment. This is what it looks like today. And actually, what does this look like to people? Any comments?
This sort of looks like a mixture between like a star and a planet.
Oh, is that right?
I don't know. It just sort of looks like that.
Well, you could almost think of it like that because it's the remains of a star, its guts, spewed out in the sky, and then this is going to form raw material for a future planet one day. I was looking for things like cotton candy. My wife, who is a textile designer, says it looks like yarn, you know. I don't know. But what this is, so first of all, what are we looking at? This is an X-ray image superimposed over an optical image that shows the stars. And the X-ray wavelengths is privy to the emission from the stellar ejecta, the guts of the star, okay? Hundreds of years after the explosion. And here's a quotation from Tycho Brahe. I mean, he was a very dramatic person. So what do you say? A miracle indeed, either the greatest of all that have occurred in the whole range of nature since the beginning of the world, or one certainly that is to be classified with those attested by the holy oracles, the staying of the sun in the course, the prayers of Joshua, and the darkening of the sun's face in the time of crucifixion. So either it was the most important thing that ever happened, or the second most important thing that ever happened, right? So contrast that with Kepler, who observed a supernova in 1604, just a few years after Tycho Brahe's untimely death, actually. And this is what the supernova looks like today. Again, this is a mixture of X-ray, which is the really colorful stuff, and then the optical you can see in higher resolution, which is not so much the stellar ejecta as the supernova interacting with the surrounding material. Kepler was a little bit more modest. The star's significance is difficult matter to establish, and we can be sure of only one thing, that either the star signifies nothing at all for mankind, or it signifies something of such exalted importance that it's beyond the grasp of understanding of any man. So it was either it's meaningless or it's the most important thing. You know, he covered his bets one way or another. This is what it looks like today. So it took hundreds of years before something happened kind of nearby. And in this case, the supernova didn't take place in our own Milky Way galaxy, but a satellite galaxy called the Large Magellanic Cloud. Now, this is an ordinary star, somewhat. You wouldn't think much of it because there are other brighter stars nearby, but you know that arrow means something's going to happen there, right? Well, what happened? Boom! Supernova 1987A, right? That star exploded. And if we go back to that region years later with the razor sharp imaging quality of Hubble Space Telescope, we see that the star is gone. And left in its place is this debris cloud. Around it is stuff not by the supernova, but actually left behind by the progenitor star system, this mass loss. And I could talk for days about that. Here's other examples of galactic supernova remnants. This is the Crab Nebula. Maybe, has anybody heard or seen this before? Heard of or seen this, the Crab Nebula, right? I actually worked with a group to make a three-dimensional reconstruction of this. Maybe I could share that link another time. And then another one it's the youngest core collapse supernova that we know of. It was never observed visibly, but this is the remains. This happened about 340 years ago. This occurred in the constellation Cassiopeia, which is pretty easy to see in the northern hemisphere. This is a Hubble Space Telescope image, and again, the different colors are tracking different wavelength regions. This is optical, and you see that it's kind of all over the place, but my research actually tries to unpack the patterns and try to understand what that informs us about how the explosion proceeded in the star that was there beforehand. Oh, this is a different perspective. This is X-ray in combination with optical and infrared. Do you see this here? That's a neutron star. The star exploded through a core collapse process, and in its central region compacted down to very dense states, forming a neutron star. Lots to be said there. Oh, and this is the three-dimensional stuff that I was talking about. Taking careful measurements of the expansion of the gas, we can make a three-dimensional reconstruction. Oh, and then sometime maybe we could do this virtual reality thing that I've been working on. So what we're doing is, so everybody puts it in remotely. There's that knucklehead me and some other students that I work with. And I can show you the three-dimensional reconstructions in this virtual environment. Let's fast forward a little bit. Yeah, there's a Crab Nebula. I'm gonna get rid of them. And then we go in this room and I can grab it and enlarge it. And then we could walk around in a virtual experience. Okay, I'm sorry, I talked a little bit too long, but I was excited to share that with you. I see we're running up on the hour time. If anybody has any questions about that.
Dan, there's a question in the chat. Two questions. Has there been a supernova since, let's see, has there been supernova since then that we have observed? So anything recently that we've observed?
Okay, great question. So yes, and in fact, okay, that we've observed. Good caveat to that question, because you know supernovae are happening all the time. In the universe, if you can hear it, there's a supernova going off every second, right? But so many are distant, we can't observe them. Now, what we can observe are the ones that are nearby. And currently, with surveys, we're able to find tens of thousands of supernovae per year. Okay? But they're extragalactic, which means they're just tiny point sources. Okay? What we really want, what's going to be really juicy, is when another one happens in our own galaxy. And I'm actually part of a task force that is on high alert, waiting for when that happens. And the supernova is associated with a lot of energy at different messengers, we call it. A lot of it is going to come through neutrinos. Maybe you've heard of this subatomic particle. The neutrinos, we have neutrino facilities on Earth, and those are going to be the first warning that supernova is imminent in our own galaxy. So this, we call it supernova early warning system. And when the neutrino facilities have their tanks light up by these neutrinos, we need to tell the community that a galactic supernova is going to happen. The answer is the last time that happened, where neutrinos were detected, was in 1987, the event that I showed you. Nothing has happened since.
One final question from chat. I'll give you a parameter to answer this. Consider looking up into the sky and seeing a full moon. If we could see a supernova, a nebula from the explosion of a star, how large, if we could see it, for example, in Andromeda, if we could see that, how large would it be relative to the size of a full moon?
Okay, very good question. I'll give you an example of the Crab Nebula. Okay, so the size, and I'm going to talk in angular dimensions. I'll ask my students, what's the size of the full moon in angular dimensions? Vic, Aled? See, they can be put on the spot too. I'll open it up to anybody. Anybody know offhand? No, it's about half a degree, 30 arc minutes. Okay, and the crab is measured in a few arc minutes. Okay, so you know, if this is what happened to my ruler, I lost my ruler. Anyway, if this is like, you know, 30 centimeters, and then we talk about 1 centimeter. So does that give you a sense of perspective? Okay. So we can actually image this pretty easily. And there's a lot of great imaging done by professionals and amateurs of these types of nebulae. So in terms of angular size, what's visible on the sky, in terms of physical space, right, they're parsecs across. Parsecs, there's 3.26 light years in a parsec. You've likely heard of a light year before, right? Time it takes light to travel, sorry, the distance light travels in 1 year. So, and it boggles me. It takes light years, like 10 years, to go from one side to another. It's so big, physically speaking.
All right, Dan, thank you very much for impersonating Professor Kepler in your video. And if for any of you who haven't watched the video, please go do that. It's pretty entertaining. I think we'll wrap up here with a couple of closing things. I do want to just pick up on something that Dan said about our physics and astronomy. Astronomy at Purdue, astrophysics. We've got a very active department. So for those of you who might be thinking about, you know, you're, excuse me, a year or two away from graduating, and you might be thinking about a school, Purdue has a very active astrophysics program. In addition to that, as my TAs here can attest, Purdue is very open and welcome to undergrad research. So undergrads here do research with professors, research groups all the time. And any of the TAs that are likely to be here now or in the future could attest to that. So if you're thinking about the place to be, think about Purdue. So there's a shameless plug.
Yeah, Dave, if I can just add quickly to that, just and please feel free to utilize us as resources as you move forward. So if I'm scary to approach, you know, maybe you want to discuss with one of the TAs, is there some link information that can be provided for them? I mean, I don't know. We'll work it out, but just don't feel, don't be shy to approach about, you know, learning more about the program. And even, I get it if you're thinking, I can't stay in West Lafayette or wherever you may be, you got to go somewhere else. You can speak to us about other programs as well. Utilize this as resources. I'm very happy to do that. I'm passionate about astronomy. Yes, I think we're doing awesome research here. There's also other areas of research that we may not have strongly here that you may be interested in. So feel free to contact us about that.
All right, thanks, Dan. So here is a note from Vic in chat. Vic is giving you her email address. If you would like to reach out, Vic is one person that you could contact. Thank you, Vic. And if you have questions, you're free. Anybody's free to email me, and I can put you in touch with Vic, Alan, Mariana, or any of the people you see here working with us in Saturday Morning Astro. So we're here to help. We have just probably one last thing, and that is we've cooked up a little competition. So we're going to throw out an option to have some fun, and you too can be a prize winner. So I think Alan has the details on this. Alan, what do you want to say?
Yeah, so Dave's got a little competition for you guys. What you need to do is find an ancient astronomer. I know there were some listed on your worksheet, but you can find other ones as well. And make either a social media profile for them or a meme. And we'll see what you guys come up with. I'm sure you'll have some great ideas. And Dave, what are they going to win?
Well, we have a little prize package, a little care package from Purdue Physics and Astronomy that we can put together. We have, for example, a moon that says Purdue Physics and Astronomy. It's not a model of the moon exactly, but it's a nice squeeze ball and it's a cool thing to put on your desk. We have a badge from Purdue Physics and Astronomy. We have a sticker, and we have, we have a mascot called Purdue Pete. I have a Purdue Pete here who will literally curl up in the palm of your hand, and you can check it out for yourself. So we'll send those out to, so we're going to have entries come in. You have until next week at this time. Next Saturday at noon will be the cutoff. So you've got a week to make a social media profile, something like, maybe a dating profile if you were looking for a date, or a meme of some kind, one page. And it could be a well-known ancient astronomer or somebody that you can research and find who's pretty obscure and interesting. So you can send those to me. You have my email address. We, among the ones that we receive, will pick first, second, and third. And each of you will receive our little care package from Purdue. So, any questions? This is for you creative types. So combine your science with your creative mind and see what you can come up with. With that, I will say thank you for being here. Dan, Professor Kepler, We appreciate your participation.
This is fantastic. Very great to meet everybody today. I hope to see you again in some way.
All right, so that's a wrap. Thank you for attending. We'll see you next time. Be free to email me if you have any other questions. Goodbye, everybody.
Good.